Morning. Morning. Can anyone hear me okay? Hello? Better? Yes? Okay. So, welcome to Econ 11. So as I sent you an email saying that you should already read the syllabus and Note 0, but I'm going to go over the syllabus very quickly, some important points. I think that what everybody cares about is the grade distribution, right? So the grade distribution is, there's two midterms, 20% each, final exam is 40%, assignments 20%, and then you have 50% extra for participation. So the midterms, the dates are April 21st and May 19th. So the midterms are already structured. It's 25% multiple choice questions, 25% true and false questions that have to be justified, and 50% of short answer questions, 10% of bonus extra. So as you can see, it seems long. They can be solved in 1 hour and 15 minutes, but it's my experience that you'll feel that it's time constrained. So there are going to be two options. The first option is that we can either have the exam half an hour before, so that the exam would start at 9. I don't know if there are people who have class before. Or we can pass the exam at 7 the same day. So we will have the exam at 7 p.m. on April 21st, at 7 p.m. on May 19th. Or the other option is we don't change anything, and the exam is already the exam is not going to change whether you choose any of the three options. But if we cannot get into any kind of conclusion, then we're just going to leave it at the time of class, and it's going to be 1 hour and 15 minutes. So I'll be sending an email about the different options today, so you can vote on them and then let me know, right? So if you have class before, then we won't be able to do that option, right? So that's about the exams. The assignments. So for the assignments, the problem sets are going to be posted every week in the class website. So the class website, you go to the course website, Spring, then Econ 11, right? And then here's the course website. So if you can see here in week 1, you already have the notes, right? And here in problem sets, you can look at the problem sets, right? So the way that you're going to turn in the problem set is, so here you have the questions, you download the questions, and then here you also have the resource for a turning assignment. So what you do is you click on there, and then here's where you'll upload your assignment. So how do you upload your assignment? Well, you have to scan your homework. There are two options. You can either use the scanner, the HP scanner that's in Powell Library or in YRL. So it's a very easy scanner. You just put everything there, and then it just converts everything into one PDF. Or the second easiest way is to download the app Cam Scanner, and then that one also transforms everything into a PDF, and then you can just upload it, right? So you can only upload one file and one PDF, so that way the TAs don't have any troubles with grading all the assignments. There are 11 problem sets. From them, only 10 will count, so we'll just take your 10 maximum grades. So it's almost one problem set per week. Finally, so that's exams. Final exam is cumulative. The final exam is on June 9th from 3 to 6. And finally, we have the 15% of participation, right? So how does participation work? Last quarter, we had also participation, but the problem was that keeping track of it's just impossible. And also just you individually participating during class, it's almost, you won't get a chance, right? So instead of that, we're going to have, I found a new platform that's called Top Hat. So the way that Top Hat works is going to let me keep track of everything, of participation and of attendance, in that way that you can all have the same fair advantage on getting those points. So the good thing is that it's going to let me not only, I'm going to be able to project the slides, and then you can follow the slides here, but you're also going to be able to do it from your computer and from your tablet or your phone. So, for example, if I want to ask one question, I would ask that question, and then everyone in their own tablet or in their own phone, they can look at it, and then even if you don't have a tablet or a phone, you just need a cellular cell phone, and then you can just text the answer also. And so that way, everyone can just do that and then participate and earn the points, right? So those would be group participation. There will also be attendance. So 5 points is going to be from group participation, right? So it's going to be that you participate while I'm asking the questions. The second 5 points are going to be from attendance. So this also lets me take attendance. If you see, I can just click here, and then you can either text the number, or you can just also click on your own respective laptop, and then that way I can take attendance. And finally, here we also have for individual participation. I can also have here a discussion, right? Where you can also let me know that you participated, right? So, for example, here we have week 1, class 1. And then here, if you participate individually during class, provide a brief summary of your answer. So the way that this is going to be very easy, because that way you always know what's your participation grade, so you don't have to wait for me to update everything. And you always know how many points you have, you know how many questions have been asked, you know everything. So that way it's better for you, and it's also better for me. So you get 5 points from group participation, 5 points for attendance, and up to 5 points for individual participation, right? So those points are extra. The only bad thing about Top Hat is that it's not free. It costs $24. So since the extra points are, and I'm not a shareholder of Top Hat, so don't worry about it. The way that, so since they're extra points, you're not forced to do it. So I will require for you to sign up for it. You sign up for it, and then you have 1 week to try it out. So today you're going to receive an email telling you about how to enroll in Top Hat, how to download the app if you want to use a tablet, and all the guides that you can use in order to learn how to use it. And you have 1 week, right, as a free trial. If you don't want to pay for it, then they can give you your money back, right? But the problem is that then you won't be able to have access to the 15 points, right? So they're extra, so it doesn't have to do anything with your grade, and also the class is not curved. So since the class is not curved, that means that you won't be competing with people that have the 15%, right? So it's the only way to keep participation manageable between 300 students, right? And also to give you an opportunity to participate, and so that the TAs are not always working, trying to figure out the points. So that's all about grade distribution. And now let me introduce you to your TAs. Do you want a microphone? No.
Huh?
Do you want the microphone? No.
I'm Anastasia. I teach Monday and Tuesday at 4. What else? Do I need to say something? No.
Hey, I'm Moshan. I teach Monday at 9 and 10, and I haven't decided my office hour yet, but as soon as I do that, I will send you guys an email.
Morning, I'm Konstantin, and my sections are on Friday, one G and also J, and welcome.
Hello everyone, my name is Alessio. I teach section C on Tuesday at midday and D on Wednesday at 4.
Hi, I'm Andy. My session will be on Wednesday from 9 to 11. 2 sessions in a row, so I'll see some of you tomorrow.
I'm Matt. I'm teaching just one section Thursday at 4. I don't really know what letter it is, but I'll probably decide my office hours during section to see what's convenient for everyone.
So all of the TAs have already been, they've already taught Econ 11 before. They're very smart, all of them. They're very good. So the worst use you can use them is as answer keys for the problem sets. If you go to the office hours and say, can you solve question 1, 2, and 3, and then just make them solve the problem set, it's just going to be a waste not only of your time, but also of their time. You should use them in order to understand better the concepts, right? Don't ask them, how do I solve this? But ask them, so I've tried to do this for question 1. What am I doing wrong? Or what other method do you think I should use, right? So in that way, you learn, and then you can apply what you've learned for the exams. Just copying the the answers from the board when they're solving them, it's not going to be efficient, and it's not going to be a good use for your time. Okay? Thank you. Very good. So for everything else, for policies on missed exams or grade appeals, the disabled students and Office of Students with Disabilities and academic dishonesty, then just please refer to the syllabus. Everything is in the syllabus. If you have any more questions, you can always send me an email, right? So now we're going to start. So if you look at the class website, you will also find Note 0, preliminaries, right? So Note 0, what you'll see is that's the level of the math that we're going to use in the class. The level this has to do with multivariate calculus, but it's not complicated multivariate calculus. It's just taking partial derivatives. That's as far as we go, right? So even though if you only learn how to take a derivative of a function of one variable, then read the notes. The notes explains how to take derivatives of more than one variable, and then total differential and some applications, right? So that's as hard as math will go, okay? Today we're going to start with Notes 1, Mathematics in Microeconomics, right? Very good. What's going to be the whole objective of the course? What we're going to have is we're going to try to learn how agents make their decisions, right? So if you go to the supermarket and then why do you decide to buy 3 apples? Why do you decide to buy 2 bananas, right? It depends on, first of all, your preferences, right? Maybe I like apples, right? Second of all is the price of the goods. Well, I need to know the price because that way I can know how many apples to buy, right? And finally, it depends on my income. It depends on how much money I have to spend on apples and bananas, right? That easy. So in order to solve those problems, we need to solve unconstrained maximization problems and constrained maximization problems, right? So let's consider, I'm trying to figure out how to turn this light off. There we go. Perfect. So consider the following problem. We have a baker that produces apple pies using apples as input according to the production function f, that is q equals f of a. The baker chooses the number of apples to buy to maximize profits. Apple pies have a price of p and the cost of each apple pie is c. Therefore, the baker's problem is, so the baker wants to maximize profits. Profits are equal to? Very good. So it's total revenue. My profits are equal to my total revenue minus total cost. My total revenue is just the price of apples times how many apple pies I sell. So P times the quantity of apple pies. And the total cost is the cost of each apple is C, and then how many apples I use, right? So we have the price, the quantity of apple pies, the cost of an apple, and the number of apples I use, right? And they're also telling me that production of apple pies depends on, it's a function of the number of apples that I use, right? So the quantity of apple pies, it's a function of the apples that I use. What do I need to do? I want to maximize, right, my profits. So I want to maximize P times Q. P times, in this case, I'm going to put F, sorry. P times F of A minus C times A, right? What am I choosing? I'm choosing the number of apples, right? Do you agree? Why? Yes?
Your unit is apples, so seeing as you want to maximize profits, you want to see how many apples.
Very good. I want to know how many apples because once I know how many apples I use, then this production function tells me how many apple pies I produced, right? And then that way, that enters into my production, right? Very good. So today, since you haven't enrolled in Top Hat, if you participate individually, just send me an email after class, and then that way I'll update the participation. Just for today. After that, if you don't have Top Hat, then I'm sorry, but there's no other way. No, I just spend my day answering emails about participation, so that's why. So I'm going to maximize my profits, and I'm going to choose the number of apples, right? So this is a very important characterization that we have to use. We have to differentiate between choice variables and parameters. That's the first thing that we have to do. Always determine what's your choice variable and what are your parameters. In this case, what's your choice variable? Apples, right? That's the variable that I'm choosing, right? The baker chooses how many apples he's going to use. So the apples are my choice variable. And then I have my parameters. The parameters are the ones that I don't choose. I take as given, right? So the baker takes those as given. In this case, what are the parameters? Very good. The price? Yes? Very good. And the cost, right? So we have P and C are the parameters. Right? F is just a function, right? So maybe F is just, we can have maybe that F is, for example, A to the 1/2, A square root of A, right? For example. So it's just a functional form. It doesn't necessarily have to have parameters, but we could have that maybe F of A equals A times B, right? Then in that case, B would be a parameter, right? So F just tells me a function. So let's try a more concrete example. So a baker produces apple pies using apples as inputs according to the production function Q equals square root of A. The baker chooses the number of apples to buy to maximize profits. Apple pies have a price of 6 and the cost of each apple is 3. Therefore, the baker's problem is. So now we're even being more concrete, right? So we're saying that the price is 6 and the cost is 3, right? And my production function is square root of A. So my problem would be maximize. I'm going to choose how many apples to buy in order to maximize my profits, which are 6 times A square root of A minus 3 times A, right? So in this case, in this more concrete example, we can see how parameters are numbers, right? Parameters are numbers that I take as given, and then I use them to solve my problem, right? Very good. So to solve unconstrained maximization problems, what do we do? Yes?
Take the derivative, equal to 0, find a local maximum.
Very good. So we're going to take the derivative of the function, and then we're going to set that derivative equal to 0. That's called the first order conditions, right? The first order condition. So when I take the derivative of a function and then I set it equal to 0, that's called the first order condition. And then that's the way that I'm going to find the maximum, right? So we have unconstrained maximization of a function of one variable so if we're trying to maximize f of x, right, then the first order condition for a local maximum is the derivative of f of x with respect to x set equal to 0, right? If we have more than one variable, if instead of having apples we have apples, and maybe he also used pears, right, to produce pies, the first order conditions are going to be the same, but instead of having just one equation, what we're going to have is a system of equations, right? So if we want to maximize a function of several variables, so unconstrained maximization of a function of several variables, then the first order conditions for a local maximum are, so now instead of having just x, we're going to have x1, x2, x3, x4, x5, x6 until xn, right? So now what we're going to have to do is we're going to have to solve a system of equations. We're going to have to solve the partial derivative of f of x with respect to xi has to be equal to 0 for all xi, right? Where x equals x1 to xn, right? So what we have there is just a system of equations. We take the partial derivative of the function with respect to each of the variables. We set those partial derivatives equal to 0, and then we solve the system of equations, right? That's what we're going to have. That's what we're going to do the whole quarter. That's essentially what we're going to do. When we have a function, we're going to take the first order conditions, and then we're going to solve the system of equations. You can say, well, I'm going to have to solve a system of 4 by 4 equations. No. Normally, it's always going to be a function. It's just going to be two variables, right? We're always going to have two goods, two inputs, and then that way it's just it's easier, right? But what I always try to do is always try to write everything, all the definitions in general, right? So in general, that means that for n goods, for n inputs, so that at some point in your career, if you look back and then you do, how do I solve a problem with 3 variables? Well, then you can just go back and then see, oh, it's the same, right? Very good. So let's go back to our problem. In our problem, it's a function of just one variable, right? So let's do first the concrete example. So the first order condition in this case would be 6 times 1/2 a to negative 1/2 minus 3 equals 0, right? Also in note 0, at the end of note 0, you can find the list of derivatives, right? Those derivatives are the ones that we're going to be using throughout the whole quarter. Essentially, it's just you have a variable to an exponent, right? Or you have the sum of two functions, the product of the functions on the chain rule, right? Those are going to be the derivatives that we're going to use. So now that I have this implies so I have 3a to negative 1/2 minus 3 equals 0. So the optimal number of apples that the baker should use is 1, right? Yes? Questions? Up till now? Yes or no? Too fast? A little bit? It's to wake you up. I'm sorry, the thing that last quarter the class was at 8, so everyone was asleep, but I think that now everyone's awake, right? So if I'm going very fast, just tell me, slow down, okay? I think that top has a function that you can put feedback and you can actually project slow down, and then we'll see how that works in order to see about the class. Okay, so this is the concrete example, but what we care about is not this one. What we care about is this example, right? The more general example. So for the more general example, what would be the first order conditions? So the first order conditions would be P times F prime of A, right? Minus C equals 0, right? And then how do I solve for A? I would have f prime of a equals c over p, right? And then this is the derivative, right? Normally everything's going to be differentiable, so you don't have to worry about taking inverses. So a star is just going to be equal to f prime c over p, the inverse of that, right? That's the most general thing, right? The most general example. Sorry. It's in that form, right? Which seems complicated, right? And then what I'm going to do with that? No, just that's the answer, right? So, for example, if we already know that the function is square root of a, if the function is square root of a, so if f of a equals square root of a, then what would be the inverse of my derivative? Well, my derivative, f prime of a, is 1/2 of a to the negative 1/2, right? Which is just 1/2 square root of a, right? So what would be my inverse? Yes?
2 square root a?
Very good. 2a squared, right?
Sorry, yeah.
Yeah. Make sense or no? Yeah?
What does FOC stand for again?
First order conditions. First order conditions, right? It's over here. First order conditions, right? Yeah? Very good. Very good. So if f is square root of square root of a, then we can just solve for a star, right? So here we have f a prime equals c minus p. So I know that f prime of a equals c over p, right? So in this sense, it will be 1 over 2 square root of a equals c over p. So so a star is going to be equal to p over 2c squared, right? Yeah? Yes or no? P, A, C over 2, yeah, squared. Right? Make sense? So let's go back again. What do we want to do? We have a baker that wants to maximize profits. He's choosing the number of apples, right? Why? Because when he chooses the number of apples, then automatically he knows how many pies he's going to produce, right? And he's taking the price of the apple pies and the cost of the apples as given. We can have the most general problem, which is on the left, and then we have the more concrete example, right? The more concrete example tells us what happens if I actually know how much each apple pie costs and how much each apple costs, right? And then we can solve it and we get a number, right? We get a star equals 1. We have the more general one. In the more general one, when we solve for a star, what do we get? We get a function. We didn't even get a functional form, right? We only got the inverse of the partial of the derivative of a function, right? So that's the most general part. Normally, we're going to have a specific form for the function. So in this case, I said, well, what if the function is square root of a, right? So if the function is square root of a, then a star is going to be a function of what? Of my two parameters, right? Of p and c. Does that make sense or no? The optimal number of apples has to be a function of the parameters. Depends on how much the price of apple pies is and how much each apple costs, right? Yes or no? Yes or no? Sure? Sure? So in one case, we have a specific number. That's when I already gave you the values of the parameters, right? In the other case, when I already have a specific form of my function, then I can solve for a general form of my result, which is a star is a function of my parameters. What happens if I now plug in the numbers? If I plug in here 6 and 3, what would I get? 1, right? So it's the same. Do you agree? That's what we're going to do. We're going to try to solve the problem of a consumer that wants to maximize their happiness subject to how much money they have and how much each of the goods cost, right? What we're going to try to determine is the demand functions. What are demand functions? Demand functions, it's how much I'm going to buy as a function of the prices, right? And of my income. So that would be this result. But then if I give you the price and income, then you can tell me, oh, well, this consumer chooses to buy 1 apple in this case, right? So that's the first part. The second part is we want to know, so now that we know that the baker chooses 1 apple, we want to know what happens to his profits whenever one of the parameters is changing. So I want to know how his profits change when there's an increase, for example, in the price of apples, right? Or how does his profits change whenever there's an increase in the cost of apples, right? So applied to the course, that would be, we want to know how the happiness of a person changes when there's, for example, an increase in prices, right? Or when there's a reduction in income. So whenever we want to learn about what happens to the maximum value of a function, what we use is the envelope theorem. So the first time is going to be complicated. You're going to say, what is he talking about? But we're going to use it all the time, and I'm going to keep using it and using it and using it and using it and using it, and by the end you'll see that you'll learn the envelope theorem. But the whole point is, the envelope theorem is just a result. The envelope theorem is just a shortcut, right? What it tells me is that in order to take the derivative of a maximum function with respect to a parameter, the only thing that I have to do is to treat the objective function, to treat the other variables as constants, right? So I'm just going to take the partial derivative of the objective function with respect to the parameter. That's it. That's the envelope theorem, okay? So I just said it once. Right now you know what it actually means. But then we're going to do, first I'm going to write it, then we're going to do an exercise, and then we're going to repeat it again and again, okay? So first of all, we have to differentiate between, here we differentiate between choice variables and parameters. Well, what's the difference? The choice variable is the one that I'm choosing, right? It's the one that I take the first order conditions. And the parameter is given. The parameter is something that it's given to me. I cannot choose it, right? The price, I cannot change the price. The cost, I cannot change the cost, right? If I go to Ralph's and then I said, oh, no, I'm going to buy this milk, but I'm going to buy it for $1. I don't care about what the price is. No, right? The price is already given. Now we're going to differentiate between the objective function and the value function. What is the objective function? The objective function, well, it's a function that I'm taking the derivative to, right? It's a function that I'm trying to maximize. Function that I'm maximizing. So in this case, it would be this one, right? It would be my profits. I'm going to call it small pi. So if you see, small pi is going to be a function of what? This is small pi, my profits. Are going to be a function of what? C, very good. Another one. P, very good. And A, right? My profits are a function of the price, the apples, and the cost, right? It's a function of both the parameters and the choice variables. So it's a function of A, P, and C, right? What's the function? P times f of A minus C times A, right? That's my objective function. What is the value function? The value function is the objective function evaluated at the maximum value. Make sense? The objective function evaluated at the maximum value. So the value function is the objective function evaluated at the maximum value. That one I'm going to call it capital Pi. I'm going to leave a space here to say what's a function of. And it's going to be the maximum over A of the objective of pi, small pi of A, P, C. So it's the maximum. So my value function is going to be exactly the value of the objective function evaluated at the maximum, right? So if I solve this problem, what do I get? I get A star, right? So that means that my value function is just going to be what? It's just going to be P times F of A star minus C times A star, right? So it's my objective function. Do I need to write bigger? No? Yes? No? Okay. It's my objective function evaluated at the optimal value, right? So for example, in this case, in the more concrete example, I had that A star equals 1, right? So what's the value of my value function? Well, I just have to plug it in back into my objective, right? If I plug in A equals 1 into my objective, then the value function is 6 minus 3, 3, right? So in the more concrete example, my value function is 3, right? What did I do? I just plugged in A star into the objective, right? In the more general example, I would have to plug in this function into the objective, right? That's going to be my value function. As you see, the optimal value, it's a function of what? What did we say? It was a function of the parameters, right? Yeah? So that means that I can write my value function as A star, that's a function of the parameters, P and C, right? So I have A star is a function of the parameters P, C, F prime of C over P to the negative 1, right? And so my value function is going to be a function of what? It's going to be a function of A star and the parameters, right? So it's going to be a function of A star and the parameters, C and P. But we already said that A star is a function of the parameters, right? CP. So in the end, the value function is just a function of what? A little bit louder, please. The parameters. Very good, right? So what's the difference? The objective is a function of the choice variable and the parameters. The value function is just a function of the parameters. Why? Because what I'm doing is I'm substituting the optimal value back into the objective. And since the optimal value is a function of the parameters, then I just have a function that is only a function of the parameters. Right? Very good. So, the envelope theorem is a result that tells us what if I want to know what's the derivative of the value function with respect to one of the parameters. So what I'm doing is I'm taking the derivative of pi A star CP CP with respect partial with respect to, for example, P, right? So I want to know how my value function, how my profits, my optimal profits change when there's a change in the price of apple pies, right? If I look at this function, right, at the more general example, do you think you'll be able to do it? Take the derivative, so I will substitute that into my objective, and then take the derivative of that. So, I mean, just, let's see. So we have p times f of f prime to the c over p minus 1, right? Minus c to the f prime of c over p to the negative 1, right? That will be my value function. Do you agree? Do you agree? And then you take the derivative of that to know how everything changes. You have to take the derivative with respect to p. I don't know, I mean, I wouldn't be able to do it, right? Would you be able to do it? It's too complicated, right? The envelope theorem tells me don't worry about it. It's not going to be that hard. The envelope theorem is just going to be an application of the chain rule. If I want to take the derivative of this function with respect to p, I just use the chain rule. What does the chain rule tell me? Well, take the derivative with respect to each of the variables and then just add them up. That's the chain rule, right? So that means that if I want to take the derivative of that function, it would be the partial derivative of pi with respect to a times the derivative of a star with respect partials, everything's partial a with respect to p, plus the partial derivative of pi with respect to p times the partial of c with respect to p, plus the partial of pi with respect to p times, this is d, sorry, d, times dp with respect to p. That's the chain rule, right? The partial derivative of c, the derivative of c with respect to p is 0, right? Very good, 0. You have f of x equals x, right? And I take the derivative of x with respect to y, 0, right? Because it says if I was taking the derivative of a constant, right? So it's 0. This would be 0. So this is 0. What about this one? The derivative of p with respect to p is 1. Very good. This is 1, right? Very good. So as you can see, when I'm taking the derivative of the value function with respect to one of the parameters, I have two effects. I have a direct effect and I have an indirect effect. The indirect effect is, well, I'm taking the derivative with respect to the parameter, but my optimal value is a function of that parameter, right? So in order to know how my value function is changing, I have to take the derivative first of the objective with respect to the variable, and then take the derivative of the variable with respect to the parameter, right? That's the first. That one is the indirect effect, right? If the price of apple pies goes up, then that's going to affect the number of apples that I buy, right? And then that in turn affects my value function. Does that make sense? That's the indirect effect. Yes or no? Again, if the price of apple pies goes up, then that's going to change the optimal number of apples that I buy. And then by changing the number of apples that I buy, that also changes my objective, right? So this one is the indirect effect. But I also have to consider the direct effect. The direct effect is how the parameter affects the objective function directly, right? If I look at it, my objective function is p times f of a, right? So it's not only that that when the price of the apple pies goes up, I change the number of apples that I buy, but also that it changes my profits, right? Now my profits are going to be higher, right? Because the price is higher. Make sense? So that would be the direct effect. This is the direct effect. Now, who can tell me the indirect effect equals? Louder? What is this? This is the derivative of pi with respect to a, right? Yes? I think we erased it. Let me see. Oh, no, here it is. We have the derivative of pi with respect to a. And then we have that evaluated at the maximum, right? Because we're always evaluating at the maximum value, right? The derivative of pi with respect to a, we already do that, right? That's the first order condition, right? The derivative of pi with respect to a was my first order condition. It's here. That's the derivative of pi with respect to a, right? This is my first order condition. But my first order condition was the partial derivative, I had to set it equal to 0, right? So this is 0. And what do I have left? I have the derivative of my objective with respect to the parameter evaluated at a equals a star. That's the envelope theorem. The envelope theorem tells you when you want to take the derivative of a value function, you're going to have two effects. You're going to have the direct effect that tells you how the objective is changing when you change the parameter. But you also have the indirect effect, which is how your optimal choice variable is changing when you change the parameter, and that in turn affects the objective, right? But don't worry, because the indirect effect is always 0. Why? Because we're always evaluating at the maximum, right? And at the maximum, that derivative is 0. So we only have to care about the direct effect, right? What does that mean for our problem? If I want to take the derivative of, I want the partial derivative of pi of a star Cp with respect to p. So I'm just going to look at my objective function, and I'm going to take the derivative with respect to p. I'm going to take the derivative with respect to p, treating everything else as a constant. So what would be the derivative of my objective with respect to p? F of a, very good. F of a. But I have to evaluate it at a star, right? A equals a star. We're always evaluating at the maximum, right? Right? So that means that I didn't have to take, oh, I erased it, I think. Yeah, I think I erased it. Yeah. Remember the horrible function that I had over here that I take the derivative with respect to? You didn't have to do it, right? It's enough to just treat everything else as a constant and take the derivative of the objective function with respect to the parameter. And then just evaluate it at the optimal value, right? So let's suppose you have a problem in the midterm that says, suppose a baker has, the baker has the following objective function, given prices and the cost of apples, and we know that in the optimum he's producing 1 apple pie. What is the derivative of the maximum profits with respect to price? So you have the same problem, and it's already telling you that the baker is producing 1 apple pie in the optimum. What is the derivative of the value function with respect to price? You have that problem over here, this one. And then it's asking you, what is the derivative? And well, it's also telling you that he produces 1 apple pie in the optimum. What is the value of the derivative of the value function with respect to price? You have it here, right? This is the derivative. This is what they're asking for, right? It will be f of a evaluated at the maximum, right? F of a is how many apple pies he's producing, right? So that means that the answer is 1, right? Yes or no? So again, the problem is telling you this one in general. In general, you have that production function, you have that f, everything is in general. what is the value of the derivative of the value function with respect to the price if I know that the baker is producing 1 apple pie? That means that in the optimum he's producing 1 apple pie. Well, I take the derivative. I know that it's f of a evaluated at the maximum. That means that the derivative of the value function with respect to price is just the number of apple pies that he's selling in the optimum. Right? Yes? Sure. So we just showed the result, right? This is the envelope theorem. The envelope theorem just tells you that if you want to take the derivative of the value function with respect to any of the parameters, that's just as if I'm taking this function, right? Everything else as constant, and I'm just taking the derivative with respect to p, right? So if I take the derivative with respect to p, it's just f of a, right? 0. But since it's a value function, it has to be evaluated at the optimum value, right? So if they are already telling me how many apple pies he produces, right? That would be f of a star, which is 1. Then this derivative is just f of a star, right? Which is 1. Let me put it this way, f of a star, which equals 1, right? In this case. Make sense? Nice result, right? Yeah.
The question gives you the function of a already?
They didn't even tell you the function. They told you he produces, in the optimum, 1 apple pie.
Okay.
Right? So if they're already telling you what's the value in the optimum, you don't need to calculate any derivatives.
Okay.
Right? Well, I mean, just one, but that's easy, right? Make sense? Good? Yes? Yes?
So then what exactly is this telling us? What did we just calculate? What is it telling us overall?
Oh, very good. So what would be the economic intuition, right, of that in that case? So let's say I want to know how, because this is my optimal, my maximum profits, right? So it's telling you that whenever, if the price changes, right, in this case, your profits are going to change by how many apple pies you sell. But that makes a lot of sense, right? So my maximum profits are going to change depending on the price, right? If the price of the apple pies goes up, how are my profits going to change? Well, it depends on how many apple pies I'm selling, right? So that's the economic intuition. That's very good. So here it's mathematics, but we're also going to try to relate it to economics. In this case would be, so what does this result tell me? Well, this result is telling me that my maximum profits change with respect to price depending on how many apple pies I produce. Which makes sense because that's exactly what I'm selling, right? Yeah? Make sense? Very good. And then you have the envelope. So in the notes you have the envelope theorem explained in a general way. So in a general way you have a function of several variables, which is also a function of the parameters, and you want to know what's the derivative of the value function with respect to the parameters, right? And it just says that in order to take that derivative, you just have to take the derivative of the objective function with respect to the parameter and evaluate it at the maximum value. That's it. Just as simple as that. Okay? Yes? If I didn't do that, then I would have to do it this way. That would every time that I have to take the derivative of the value function, I would have to do it this way. Take the derivative with respect to the choice variable, and then the derivative of the choice variable with respect to the parameter, and then this derivative, and then this derivative, and then I have to, right? The envelope theorem just tells you, just forget about everything else, and just take into account the direct effect, the derivative of the value function, of the objective function with respect to the parameter, right? Yes?
Just going back to the chain rule part, when you take the partial derivative of pi over the partial derivative of state, why is it 0 originally? Cancel that to 0 at one spot, but then the other spot.
So it was 0, it's because when I solved the problem, I calculated so in this case here, the first order condition, what did I do here? I took the derivative, remember, this is small pi, right? This is small pi, right? Small pi. So it would be the derivative of small pi with respect to a, right? That's what I'm doing here. And that I'm setting it equal to 0, right? So that means that at the optimal value, that derivative is 0, right? But that's exactly what I'm doing here. Here I'm evaluating at the optimal value, right? So that's why the derivative is 0, right? Very good. But that's a very good question. That's why it works, right? It's because at the optimum, the derivative is 0. Very good. So that has to do with unconstrained maximization. Now we're going to talk about constrained maximization, which is the important one, right? Which is what we're going to be doing the whole quarter. So instead of having the problem of a baker that wants to produce, that needs to choose how many apples he needs in order to produce apple pies, we're going to have the same problem, but now the baker, we have now the baker, same baker from the envelope theorem question now uses green apples and red apples to produce apple pies according to the production function f of g of r, and the price of green apples is PS, the price of red apples is PR, and he has a budget of $B to spend on apples. The baker wants to maximize his production, and then what does he solve? So now the baker wants to solve the following problem. He's trying to maximize his production, which is now a function of green apples and red apples, but now subject to, he has a specific budget that he has to spend on green apples and red apples. So the price of green apples was PG times G, plus the price of red apples was R times R. That has to be equal to B. So that's my problem. First of all, which are my choice variables? G and R, very good, G and R. So how do I differentiate with choice variables? I put them below the max, right? My choice variables are G and R. What are my parameters? Very good. Prices and the budget, right? The budget is also, I don't choose it, right? The budget is also a parameter, right? So I'm going to put them here, parameters, PG, PR, and B, right? Very good. How do I solve this problem? Well, I mean, I could take the constraint, right? Take the constraint and then solve for G, and then plug that G into the objective function and take the derivative, right? Can I do that? Yes, right? Do you agree or no? I can just take G here, solve for G here. So you have G equals B minus PR over R over PG. Take that, plug it into the objective, and then I would just have a function of one variable, right? Of G. And then take the derivative of that with respect to G, set it equal to 0, that would give me the value of G, and then substitute it again to the constraint to get the value of R, right? Make sense? That's one way to do it. Instead of that, what we're going to do is we're going to use the Lagrange method to solve constraint maximization problems. Okay? So what is the Lagrange method? I'm going to tell you in general right now, and then the TAs are going to solve one exercise about it. They're also going to solve an exercise of the envelope theorem, right? But that's the method we're going to use. So today what we've seen is just methods. First was the envelope theorem, and then this is just going to be another method, right? The method is called the Lagrange method. What I'm trying to solve is the following problem in general. Maximize f of xy. I'm choosing x and y, subject to g of xy equals c, right? That's going to be the problem in general that I'm going to try to solve. The Lagrange method has two steps. The first step is to write the Lagrangian. The Lagrangian is just a function. So what I'm going to try to do is I'm going to try to convert that constraint maximization problem into an unconstrained maximization problem. Why? Well, because I already know how to solve unconstrained maximization problems, right? That's what we did in the beginning. How do I solve unconstrained maximization problems? I take the derivative of the objective with respect to the choice variable, set them equal to 0, right? That's how I solve it. So in order to transform that constrained maximization problem into an unconstrained maximization problem, the first step is going to be to write the Lagrangian. So step 1. Step 1, write the Lagrangian. Write the Lagrangian function. The Lagrangian function is always going to be the same. It is never going to change. It's always going to be the same formula. I'm going to denote it as L. And it's going to be a function of my choice variables. And I'm going to add an extra variable. So it's going to be a function of x and y. And I'm going to add another variable. And this variable is very important. This variable, I'm going to call it lambda. So I'm adding that variable, which is lambda. Which I'm going to call the Lagrange multiplier. The Lagrangian function is always going to be equal to my objective function plus my new variable lambda times the constraint set equal to 0. That's going to be my Lagrangian, always. If I have a constraint maximization problem, then the Lagrangian is always going to be the objective plus the new variable that I'm adding, which is lambda, times the constraint set equal to 0. So in this case, it would be L of x, y, and lambda equals f of x, y plus lambda times c minus g of x, y. Right? So the first step, technically it says add an extra variable, call it lambda, and write the Lagrangian function. Lagrangian function. And then step 2 is very easy. Step 2 is just going to be solving that unconstrained maximization problem. So the second step is going to be to maximize the Lagrangian. So instead of trying to solve this problem, what I'm going to do is going to be this. I'm going to solve the following problem, which is maximize the Lagrangian function, x, y, and lambda, with respect to x, y, and lambda. Which I know how to do, right? That's a non-constrained maximization problem. So what do I have to do? I just have to take the derivative of the Lagrangian with respect to each of the variables, with respect to x, with respect to y, and with respect to lambda. And then that gives me a system of equations, right? Yeah? Make sense? So in this case, in my more concrete example, the first step would be write the Lagrangian, right? So it would be L of g, r, and lambda equals f of gr plus lambda b minus pgg minus prr. Right? That's my first step. And then my second step is, well, I have to take the derivative of the Lagrangian with respect to each of the variables, right? So now I'm trying to maximize the Lagrangian, g, r, and lambda. So I have g, r, and lambda. In order to do that, I take the first order conditions. So it would be the derivative of the Lagrangian with respect to g is f, partial derivative of f with respect to g minus lambda pg equals 0. Derivative of the Lagrangian with respect to r sorry, is the partial of f with respect to r minus lambda pr equals 0. And finally, the derivative of the Lagrangian with respect to lambda is just PGG minus PRR plus B equals 0. Right? I have three equations, three unknowns, so you just have to solve the system of equations, right? Why does the method work? So it's a method. Once you're there, then I give you a function and then it's just solving a system of equations, right? Why does the method work? Well, if I look at this, at the partial derivative, when I take the derivative of the Lagrangian with respect to lambda, what do I get? What do I have over there? The constraint. Very good, right? This is just my constraint, right? So my last first order condition, what it's telling me is, well, I need the values of R and G that satisfy the constraint, right? So once I choose the values of R and G that satisfy my constraint, what do I have? If I satisfy the constraint, I just need to find now which values actually maximize my objective function. In this case, it's f, right? So here, this one is satisfying the constraint, and then once I satisfy the constraint, once I'm here, if I look at it, I'm just solving the unconstrained maximization problem, right? I'm choosing which values of G and R actually maximize my objective function, right? So that's why it works. It works because my last first order condition is just my constraint, right? So from all the values, I'm choosing those that satisfy the constraint, and then taking those values, I'm taking the ones that actually maximize my objective, right? Make sense? Yes?
For the partial derivatives with respect to G and R, where does the minus lambda times PG minus lambda times PR come from?
So I'm taking the derivative of the Lagrangian, right? With respect to G? Yes? So it will be f prime, well, the partial derivative of G, f with respect to G, right? Then I go here. The derivative of B with respect to G is 0, right? And then here it would be minus lambda times PG, and here is with respect to G, so that would be just PG, right? That's why I have PG here. Right? Yes? And the same with R, right? With R, everything would be 0, 0, and then the derivative of this with respect to R is just PR, right? Here, right? Yes? Very good. Any more questions? So again, this is just a method, right? If I have even more concrete example, maximize, right? Let's see, let me see one. X squared plus y squared subject to x times y equals 3, right? The first step would be the Lagrangian, x, y, and lambda equals x squared plus y squared plus lambda 3 minus xy, right? The first order conditions would be the derivative of lambda with respect to x is just 2x minus lambda y equals 0. Derivative of the Lagrangian with respect to y would be 2y minus lambda x equals 0. And the derivative of L with respect to y would be 3 minus xy equals 0. Right? Sorry? I didn't hear that. Sorry? Oh, yeah, sorry. Thank you. Lambda. Right? You have the system of equations. So, for example, this one tells me that x equals 3 over y. Yeah? I can plug it in here. And I have 2y minus lambda 3 over y equals 0. Plug in here. The 6 over y minus lambda y equals 0. Right? And I just have two more equations, two unknowns. And then I solve them, and then I get y and x, y and lambda, right? I think this one was too hard. We just pull it out of my mind right now, so maybe that's why it was so hard. Let's see. From the first one, we get lambda 6 over y minus lambda equals lambda y. So y squared equals 6 over lambda, right? Perfect. And then I just plug it in here, and that way I can get the result, right? I'm just showing you how to actually do it, right? But it's, I mean, the things that I see a lot of confused faces, like, and then what do I do when I get there? Well, it's just solving a system of equations, right? Yes? Very good. So, this is just the introductory class. Maybe I scared you a little bit. But the thing is that these are the methods that we're going to use. The first of all is how to solve a non-constrained maximization problem, right? And that is just taking the derivative of a function, right? The second thing is, well, now that I know what's the optimum value, I want to know how the value function, the objective evaluated at the optimal value, changes when I change a parameter. The result was, well, don't worry about any weird second order effects. Just worry about the first effect. Just worry about the direct effect. How my objective changes when the parameter is changing, right? Finally, the problem that we're going to solve all the time is going to be a constraint maximization problem. So we're going to have an objective function where we have subject to a certain constraint. So for example, for our consumer problem, my constraint is going to be exactly my budget, right? How much I have to spend on apples and bananas, right? How do I solve that problem? I solve that using the Lagrange method. The Lagrange method just tells me, first step, write the Lagrangian, right? Second step, take the first order conditions with respect to the Lagrangian and solve the system of equations, right? That's exactly the Lagrangian. So, next class, I'm just going to continue. I just have to finish a small part of this, which has to do with the envelope theorem. Shh, it's not over yet. I still have 5 minutes, or 2, 3. Envelope theorem for constraint maximization. That's what we're going to do. It's very easy, and we're going to start right away with our first topic of the quarter, which is preferences and utility. So next class, bring notes 2, and so today you're going to receive an email about Top Hat. So please enroll for Top Hat for next class. It's going to be very important. So next class we're going to start using it. You'll see how it works, and then after that you'll decide whether to keep it or